Last but not least, talk of the day, of the session, we have Mainak Singha telling us about ZF7 quasar population.
You can use this if you prefer.
Sure, it's fine.
There's a laser printer here. So if you press and hold, there you go.
Thanks, everyone. My name is Mainak Singha. I'm a postdoc at NASA's Goddard Space Center. So today I'll be talking about like two of our recent papers combining into one talk, which is spectroscopic forecast of Z7 quasars population enrollment. So this talk will be divided into two parts. Part number one, like why our spectroscopic identification of Z greater than 7 quasars are absolutely essential, and followed by what we have learned from our past research. And number two, what have we done to build a pipeline to actually hunt for this Z greater than 7 quasars. So this starts with a really controversial topic: who dominated the reionization? I know that's a very, very debated question. So over the last many decades, many different papers been arguing about whether it's stars or active galactic nuclei that provided the most amount of photons in ionizing the universe, right? So even though there are papers like Maddow or Yalongo who suggested agent could actually dominate reionization, but most of the consensus being towards now it's mostly the photons from the stars that did most of the heavy lifting in reionization. Even though there are some simulation work, for example, Hassan in 2018, as you see in the right plot, they're saying agent could at most provide 50% of the ionizing photon budget. However, they are skeptical that this could actually violate a lot of constraints. Now, perfectly fair, but there are some important nuances. Number one, so a lot of the reionization studies do only take into account of bright quasars, and at high redshift, their number density is extremely low. So if you have very sparsely populated quasar, they cannot do much work, right? Perfectly fair. Number two, if you assume, for example, fine, you have a lot of bright quasars for some miraculous reason, but in the literature, what's been done is the escape fraction of the hydrogen ionizing photons being always assumed to be the one, and that's basically for only few sources. So the problem in this case becomes is if you assume that all kind of AGN would be basically getting out 100% of the photons they produce, you're going to end up over-ionizing the universe, and that's why the AGN only models really disfavored. Now another key limitation is a lot of these studies are in none of this agent feedback was not considered, but in high redshift we've seen that there are agent-driven outflows. So these two processes is really not super disjoint. So there is actually an inner link between this, and that's not really taken into account. So setting the stage, what we did, motivated by all these limitations, we really wanted to do our own independent study and make a compilation of all the agent luminosity functions from GeoPhysics studies. So we do see that GeoPhysics showed this rise of faint agent past redshift 4, which we know the low rare dots, they're actually dominating the active supermassive black hole population at the faint end. But we also see that little red dots are not the only populations that's prevalent. You have their non-little red dot cousins, the faint broadline AGN, that's actually 10 times more higher than the little red dots. And furthermore, you have the type 2 or the dust obscured AGN, they're even higher between redshift 4.5 and 6.5. So now the thing is, and this agent population is about 10 to 4 times higher than quasars. So the fact that all these different kind of massive black hole population exist, they'll start contributing in some sense in the ionizing photon budget, right? And number two, so AGN feedback or AGN driven outflow used to be widely considered a local only phenomena. Not the reason that like the high redshift agents cannot drive outflows, but the reason that most of the studies that IFU data were like mostly widely available in the local universe. But after GF's been dropped, we are seeing that like the outflows being present in across like all the redshift. Even right now, they are reaching past redshift 6, 7, and oftentimes their spatial extents are over like a few kiloparsecs, and whereas we are seeing like they're reaching several hundred kilometers per second. Now, here's the thing. The outflow from local universe studies, we have seen that the luminosity of the outflows and the size of the outflows are related. So there's a paper came out by Yong-Haku's group in 2018. They established such a correlation exists. Now, if you have dwarf galaxies, which is often true that in high redshifts, you have a huge number of dwarf galaxies, which is like a few less than 1 kiloparsec half-light radius, and an outflow reaching out of several kiloparsecs, there's a good chance that this outflow could break out of the galaxy, remove part of the ISM, and in turn, that would basically create the ionizing photon to leak. So that's the whole game that's going on. So what we want to do, like, take this real complexity into account and really find out what's going on. So for the sake of time, I'm not going to give the entire description of what we did, but I want to highlight our results. So what we found, once we take outflow into account and we make a grade of galaxies like hydrogen ionizing photon escape fraction from starting about 3 to 20%. 3 is like often that you say there's not a lot of line one continuum photons being escaped from these galaxies. 20% like there's a really decent number of photons being escaped from these galaxies from this all the literature. What we find is AGN at least contributes over like a 31% with ionizing photons past redshift 5. But that's when galaxies have an escape fraction of 20%. But if you take much more conservative approach, conservative numbers from this galaxy, for example, Popovich et al. Suggested like it would be less than 5%, then the number rapidly goes up on the AGN side, and at some point it reaches about 75% of the ionizing photon from active galactic nuclei only. Now, the model could be unconstrained if you don't have any guardrails. So what could really act as a guardrail here? So the hydrogen photoionization rate, or at the Lyman hypothesis, consider that gives a good idea like what's really true, because you just cannot create a model that could basically create as many photons as it can to ionize the universe. So what we really find is, long story short, if you have a galaxies have escape fraction about 3 to like 5%, and you have an agent, you can stay perfectly within Lyman alpha forest and ionize the universe, and nothing's gonna break down. So agent contribution is possible. It's not that they're negligible. Right now, GFST came out, and we are seeing that their numbers do go up, and they do drive outflows. So combining all this, agent may have a significant impact in ionizing the universe. Now, that's not the full story, because all this coming from a handful number of sample, and we have no idea like what's the true agent population in the high redshift, and that's where Roman is absolutely necessary. And number 2, this is between redshift 4.5 and 6.5, and reionization was accelerating like past redshift 7. So what was happening then? What was the agent contribution? And that's why we wanted to really focus on finding redshift 7 quasars, whether they are brighter, whether they're faint, and see like whether they could actually have a significant contribution. So the high latitude wide sky survey is a medium tier, which gives us 2415 squared degree, and you get both the quantum spectroscopy with high resolution, and you have the imaging. That's a fantastic opportunity to really like probe down, go deep enough, but also wide enough to understand their population. So what we did, we simulated the quasar population with the quasar spectra with our in-house Grissom simulator called Espresso, Gabriel Pillay et al. 2026, and this is like that's where we just submitted this paper to AppJ. So what we did? So after we ran the Quasar simulation, we added the Poisson noise based on the exposure and timer highlighted sky survey, and also what we are trying to basically see whether at high redshift, once we recover the quasar spectra, are these similar to the contaminants, for example, brown dwarf, red galaxy? Why? Because like these sources could also be compact, or in the color space, they could also overlap with quasars. The only way we could discriminate is when you look into the spectra, and that's why the spectroscopic is so important. And turns out spectroscopy is actually the decisive factor when you want to distinguish from quasars, from contaminants. And what we see, we're actually going down like past J-band magnitude 25.5. So in which case, the imaging cannot give you the right answer. Once you combine imaging as a prior and spectroscopy, you really see that you can discriminate the faint quasars from contaminants and really start to probe the faint quasar population past Z redshift 7. So this is my last slide. I'll be so looking ahead. So we got our cycle 1 Roman proposal approved, where we will be doing this work no longer with simulated data, but with real data. So what we really want to do, we want to go past J-max 25.5. We want to go down as faint as possible. So at that point, your optimal extraction will start take out information, and you'll start to basically start to have hallucination, what's really in there. So we are building deep learning algorithm with an intern from Brown University, Peijun Huang. So our early results, we have reached J-max 24.5. What we're doing here is, once we create a noisy data, we slowly removing the noise to really get back the ground truth. And what it really enables is, once you make it aware of physics, what should be preserved and what's not, you can really unlock the faint regime, and the neural network could actually see what could be the actual source that's sitting right there. So I'm really excited that once Roman takes the data, we can deliver so much to the community. And yeah, I'm gonna leave my concluding slide, and thank you so much.
Questions for Mainak? Kimby?
Sorry, this is also kind of related to one of the earlier talks, but with your analysis, do you have a sense of what the duty cycles for these between radiative versus mechanical mode for AGN are? Is that completely out of scope?
Sorry, you said in our analysis?
Well, in these types of studies, the duty cycle between, say, radiative versus mechanical mode.
Okay, yeah, we do radiative-driven wind. So the reason you can have multiple different ways to drive a wind, right? So we took on the equation-driven wind, where you say over a 30%, you're absolutely going to have a wind, but the chances goes up the moment your air-to ratio goes up over 1%. This will become really efficient. So based on that, what we do, and afterwards, whether if you have a certain size of galaxy, whether the outcuts big enough to actually break out and remove the part of the ISM.
Other questions? What kind of signal-to-noise ratio requirements do you need from Roman?
I think we're just aiming for at least signal-to-noise ratio 3 in the emission lines, not 5. But if you're really going for faint quasars, you cannot have signal-to-noise ratio of 5. So I think once you go past J-max 25, I'm happy with 3. And some points we see at 2, there's something picking up, and that's why you really need to be very, very careful if that's an artifact or that's a real signal sitting in, right?
Other questions for Mainak? If not, then let's thank Mainak again.